It is my pleasure to co-chair this panel with Dr. Ramya Sunder Raman. Unfortunately, we had a couple panelists who weren't able to make it due to health issues with family or themselves. So we will be taking the lead on presenting on the clean air challenges and opportunities for India. I wanted to start with introductions. Ramya, can you do your introduction?
Sure, I can do that. So I'm a faculty member at the Indian Institute of Science, Education and Research in Bhopal. I'm a chemical engineer by training, but I work in atmospheric aerosols, and my specific interest really is on aerosol field measurements, characterization, physicochemical properties, really understanding their transformations in the atmosphere, and sort of most importantly, getting at the source specificity of their impacts. And by impacts, I mean air quality impacts, health impacts, climate impacts. And I do that by focusing on these specific elements of, methodology development, both for characterization and the data analysis. So that's about me. Thanks, Peter.
Thank you. And I'm Pete DeCarlo. I'm an associate professor of environmental health and engineering here at Hopkins. Similar research interests to Dr. Sunder Raman, where field measurements are a key component of what we do. We use advanced instrumentation to measure the chemical composition and size of ambient particulates and gases. We also use this in a source emission characterization, spatial measurements of air pollutants from vehicles. Coincidentally, one of the instruments that we have in my lab was flying during the CAPEX study that was just mentioned for cloud seeding in the previous panel. So there were some ties to that too, and then also interested in the science policy interface in my research. So I want to just kind of set the stage in general for air pollution and air pollution impacts. We talked previously, and the previous panel just talked about the impacts of particulate matter and aerosols on climate. They also have a very significant impact on health. And so we're going to be focusing more on that in this particular panel, but keep in mind that these same particles are having these two similar effects. And a point that we'd like to make is that air pollution doesn't just impact your respiratory system and your cardiovascular system, it impacts all body systems. There's evidence showing it affects the neurological system, reproductive system, in addition to respiratory and cardiovascular systems. And it's often PM that we associate the most health impacts with and mortality with, but other pollutants, NO2, ozone, SO2, PAHs are also known air pollutants that have health impacts and known health impacts. So we have to look at air pollution as a whole, even if the majority of impacts do tend to come from or are associated with particulate matter. World Health Organization's somewhat recent estimates basically indicate that 8 million people per year suffer premature mortality from exposure to ambient air pollution and indoor air pollution, and roughly split half and half. Their most recent guidelines suggest that about 91% of the world's population lives in places where air quality exceeds their recommended limits. And this is everywhere. This isn't just in South Asia or India. This is in the US as well. And again, PM 2.5 or particulate matter that's less than 2.5 microns in diameter drives most of the adverse health impacts that we observe for air pollutants. It's also what was just talked about in the previous panel, what's modifying cloud properties and has some indirect and direct effects with the radiative balance of the Earth's climate system. I'm going to just step through a couple points before we get on to some of the more data heavy aspects of our discussion. But a recent paper in 2019 took data of PM 2.5 annual concentration data for 652 cities and developed a curve to indicate the percentage difference in mortality based on PM 2.5 concentration. So as you increase PM 2.5 concentrations on an annual average basis, you have higher mortality rates. It's not a pure linear function. It has some turnover at the top, but the point being higher concentrations lead to more deaths depending on where you live. And so this is data from cities, and this is just total PM mass. And I think as we get into the panel, there's also going to be discussion on PM composition and how that can also be important in the context of health and in climate. So bringing this into kind of a regional context, this is a paper by Josh Apte and colleagues, and what it's showing is on the x-axis of both of these figures is the annual average PM 2.5 concentration from modeled PM 2.5 fields across the globe. And you can separate that by country and see what percentage of the population in this top plot lives in concentrations above 70 micrograms per meter cubed, less than, and we can see kind of where India fits in the context of this discussion, this conference actually spans multiple different quintiles of concentration. There are areas of India that have low concentration, areas that have kind of moderate, and areas that have high. And it depends on where you are and where your population is and what those exposures are. And the higher the concentrations, remember, the more chance of mortality. And so when you then take that population exposure and multiply it by that function of higher concentrations leading to higher mortality, you start to see the attributable deaths by country due to higher populations. So this is going to weight the higher concentration population higher, and you have more death associated with ambient air pollution at these higher concentrations compared to lower concentrations. And so India is kind of in the middle, and parts of India are certainly moving into where the US and Western Europe are, but there are parts that are certainly at higher levels that bringing concentrations down will certainly have improvements in life expectancy and reductions in mortality. It's not uniform, and another part of this paper shows the attributable mortality density. So this is highlighted, the colors, the hotter the color, the redder the color, is a higher number of attributable death per kilometer per kilometer squared per year. And so you can see the Indo-Gangetic Plain up against the Himalayas, where there's a large population, as well as trapping of air pollution. It can't really get over the Himalayas, and you get a buildup of air pollution in these regions. And so that leads to some of the higher density of attributable mortality in this particular region, going out over to the Bay of Bengal. And so this gives us an indication of where the mortality is happening, and in areas that don't have as much attributed mortality based on lower concentrations or lower population. And so this is just another way to visualize what we see in terms of where the death is happening. And this is just one endpoint. Again, remember, PM doesn't just cause premature mortality, it also has a whole host of other health effects that we're worried about. So where is all the PM coming from? There's primary PM, and when we think of primary PM, we think of emissions directly into the atmosphere. And so these are typical primary sources of particulate matter that are going into the atmosphere. It can be open air cooking or cooking indoors. Using biomass leads to a large emission of particulate matter. Industrial things like brick kilns, burning of waste in trash fires. Traffic emissions are also something of concern. Agricultural burning isn't pictured here, but it's another very big important source in South Asia that we have to think about. And other pieces to consider in this is which ones are controlled kind of at the individual level. So cooking is a very personal thing, and how people cook is something that requires an individual to make that decision. Some sources are also industrial. So if there are industrial sources, those are things that have a different potential for control. You have control at the governmental level, where you can enact policies that specifically target certain sources. And so different policies and incentives are needed to control the various pollution sources and the direct emissions. There's also secondary particulate matter that's not shown here. Those are particles that are formed through chemical reactions in the atmosphere. And so along with all of these direct particle emissions are gases that can be oxidized in the atmosphere and form additional mass in the atmosphere and interact with both health and climate impacts. My group has done characterization of emission sources in South Asia, along with some ambient air monitoring, focused mostly in Nepal, but the South Asian sources are kind of cover up most of South Asia, and they're relatively similar across the region. And so some of the work that we've done has looked at the chemical complexity of PM emissions. So at source, what's going directly into the atmosphere of these primary emissions? And we've looked at things like cook stoves or mud stoves with twig, hardwood, or dung used as the primary fuel for cooking. We've looked at crop residue burning, which again happens often in the wintertime, and what the chemical composition looks like from that. Brick kilns, irrigation pumps, motorcycles, garbage burning. All of these things have different chemical compositions and different emissions to the atmosphere based on how efficiently they burn. And so getting fingerprints of these different sources allows us to look at ambient data and try to understand what sources are contributing to ambient air pollution. And that's one of the things that my group does, and we've done. In addition, the instrument that we have also does size resolved measurements. And so we can look at these emissions and see when they're emitted into the atmosphere, what is the size range that they're typically emitted in. And this is important both in health. How far particles can penetrate into your lungs is dependent on the size of the particles. And it's also important in the climate context because the size of the particles, the larger they are, the more, given the same composition, are more effective cloud condensation nuclei. And so understanding the composition as well as the size play an important role in both the climate and the health aspects of these emissions from these different sources. And so we can build out this information on the various sources and the sizes of these sources, the size distribution of emissions in order to better understand their impacts locally and regionally. Finally, the mass spectrum that is generated from all these sources does provide this kind of chemical fingerprint that allows us to pull out from ambient data sets when we're measuring just in a city or something, the relative contribution of different sources. And there are subtle differences between all of these different mass spectra that I'm showing here. I don't expect you to understand or really care about them, but we can use statistical techniques to start to pull apart in an ambient data set, what are the key sources? And what we typically find is it's a big mixture. And there's often not one dominant source unless you're very, very close to a particular source. It's usually a big mix of many different things. And so understanding what those sources are, what their contribution is, both seasonally, time of day, and over a particular area, help us to design policies and ideas on how to control them moving forward. So I think that's the end of kind of my introduction, and I'm going to turn it over to my co-chair, Ramya, for a deep dive into India-specific monitoring questions, and then we'll have a discussion at the end.
So thank you, Peter, and thank you for inviting me to co-chair this panel discussion. And like Peter said, it's unfortunate that we sort of lost our panelists to health emergencies, but we'll hopefully give you a flavor for what these discussions sought to achieve in terms of both giving you a flavor for the complexities of, achieving clean air and the PM focus, India-specific issues, and what might be a good way forward. So Peter's already spoken to you about primary and secondary particles, size distributions. In some senses, he's really spoken about the complexity of atmospheric particles. And they're almost diabolic in a way. It makes them intellectually challenging to understand, but that also really poses a lot of problems. What I have here is a schematic that should help motivate what sorts of measurements are appropriate to address what kinds of problems. So we have a sort of XY plot here, and on the Y-axis, you go from primary aerosols to secondary aerosols in multiple sources. And this sort of shows you the share of primary versus secondary aerosol in these sources. For example, sea salt is almost entirely primary, whereas biogenic emissions are quite secondary dominated. On the x-axis, you have a time and space scale going from the source emission local scale all the way up to the continental scale. And these pink swaths sort of indicate the relative importance of particulate matter versus the gas phase compounds, gas phase components, and or the removal mechanisms, right? So what I really want to tell you through this schematic is that there is a lot of complexity, not only in the sources, the mix of primary, secondary particles, the sizes that they might be associated with as a consequence of these various mechanisms, physicochemical transformations that you see happening from the source as it gets transported. And understanding each of these processes then and the scales at which you try to understand them dictate in some senses what the relevant measurement technique would be. Peter spoke to you, for example, about GCMS measurements, highly time-resolved measurements. We typically talk about filter-based, time-integrated bulk aerosol measurements. There are also low-cost sensors that help track some of these particles, and which one is important or relevant where really depends on what is the question that you're trying to understand. As if this were not enough, and specifically because aerosol climate health nexus has been spoken about in the previous panel, as well as some by my co-chair, I just want to call your attention to something here. Let's look at a hypothetical scenario where we have the same mass and number concentration of, say, 100 nanometer particles with 50% ammonium sulfate and 50% hydrophobic organics, right? Now, these particles can exist in different mixing states, an internal mixture, an external mixture like this, and another mixing state that you can see here. What these mixing states do as far as climate relevant properties and specifically their ability to serve as cloud condensation nuclei is now dictated by the mixing state. So here's a brief snapshot of the regulatory environment in India as far as air pollution in general and particulate matter is concerned, going all the way from 1905 through to the last couple of decades. So the very first NACs, or air quality standards, were implemented in 1982, and total suspended particles, or SPM, was what was regulated then as far as particulate matter was concerned. This was revised in 94, and we included something called RSPM, the PM10 component, revised again in 2009 to include both PM2.5 and PM10. We are due for a revision in the next couple of years, and there's intense review going on for revising the National Ambient Air Quality Standards. So with this sort of background, I want to call your attention to the NACs currently in vogue. And you will notice the regulated pollutants here. And there's something called ecologically sensitive areas, sort of like the class 1 areas in the US. And you will see we have more stringent standards for these eco-sensitive zones compared to industrial, residential, rural, and other areas for just SO2 and NO2, not for PM10 or for PM2.5. Okay? So I just want to sort of call the attention of the audience, the panelists here, to the fact that it might actually be relevant to look at whether or not it's meaningful to have more stringent PM standards as well for these eco-sensitive zones. This is just a snapshot of results from my group. We did a sort of small study at what's a national park in Bhopal. This is a very small geographical area national park, so not really fully representative of other eco-sensitive environments in India, but this should still give you a flavor for, what the PM concentrations are like and how frequently they exceed the air quality standards that are fixed at the same level as the other zones. So this is one worthwhile pursuit in examining whether or not more stringent PM standards are required for eco-sensitive zones, given their potential impacts on the flora and fauna. Now let's look at briefly the status of PM monitoring and additional monitoring requirements. Some of this information is dated, some of this is more recent things that I picked up in the last 50-20 minutes from the Central Pollution Control Board website. So we have about 883 national air quality monitoring stations as of the 15th of September this year. Of these, about 271 seem to be measuring PM2.5 spread across 122 cities and towns. And the National Clean Air Program is a massive countrywide effort, a commitment by the government to really enhance air quality. And one of the goals of this program is to augment PM2.5 measurements to all 883 stations and hopefully increase these NAMP stations themselves to about 1,500 by 2024. This is all really great and it's an effort in the right direction. But just for perspective, if we look at what the population density dictates in terms of having, a reasonable spatial distribution and number of stations to really understand aerosol health effects better, that would amount to about 4,000 to 5,000 stations across India based on CPCB recommendations. Now, this is all great, but let's look at, what more mature air quality programs, specifically from the regulatory perspective across the world and specifically US, tell us about what is a good sort of sustainable model for making measurements. Should we go time integrated measurements largely for regulatory purposes, with it complemented by some near real-time measurements in air quality hotspots, zones where we have multiple sources, where one might need to better understand the atmospheric processing and transformations? What is a meaningful balance to get mechanistic understanding while also providing adequate spatial density to make regulatory decisions more meaningful? If you look at the US example, you have the CSN and the improved networks. The improved sites have remained at about 160 from 2004 or so, but the CSN sites have reduced from about 250 in 2005 to 145 in 18. I'm sorry, I didn't have the opportunity to look at what the most recent numbers are, but this drop is ascribed to budgetary constraints. So perhaps there's something for India to sort of look at in planning sustainable, networks, number of stations, etc., that we can adequately set up and run to support regulatory compliance decisions. And it's also very, very clear that our planning should now distinguish between research needs, regulatory needs, and what spatial density is appropriate for such things. I'm going to quickly draw on the example of a project that I'm involved with, a coordinated national measurement effort, 22 institutes, 45 PIs and co-PIs, coordinated and led by Professor Raman at IIT Bombay, with other coordinators from various IITs and the National Atmospheric Research Lab in India. And this is a program that seeks to look at a reconciliation of the bottom-up and top-down approaches in, understanding aerosol, specifically carbonaceous aerosol, air quality, and climate effects. I'm just presenting this as a model for discussion, in that some of the ideas that might emerge from these discussions can feed into or enhance this broad framework that is set up. And perhaps this will even help us identify research priorities, where funds should go, and etc., to really make meaningful air quality improvements and enhancements. The goals of this specific program are really to do with reducing current uncertainties in sectoral emissions, specifically of carbonaceous aerosols, source identification and quantification, estimating the impact of aerosols on various climate variables, and of course, evaluating secondary aerosols, both organic and inorganic. And this is the overall framework of this project. Let me move a little bit further and talk to you very briefly about each of these work packets. Work packet 1 is to do with emissions inventory building. This is a massive exercise with thousands of surveys across the country in various sectors, together with the emissions factors for speciated entities of PM 2.5. So this is really generating a national emissions inventory and providing something akin to the US EPA's speciate library for use in various receptor models. All of this work and the setup is detailed in this manuscript here, 2020 BAMS paper that sets up the COLIS project and its various components and goals. The other component, which is work packet 3, is really a multi-model exercise looking at aerosol-induced air quality and climate impacts, various participants, various models participating in these ensemble exercise, and the simulations for the participating RCMs and GCMs, special experiments that are set up in this exercise, as well as the emissions that we use. And these emissions will also be the national, we are of course using the smog V1 now, which is a national emissions inventory. The models will also be run with the emissions inventory that is generated within the scope of this project. The other component is the measurement component to support the receptor modeling effort, focused on carbonaceous aerosols, but also measuring all of the other components. We developed a sort of methodology to set up a network that will meaningfully capture regional background aerosol and which is not very heavily influenced by urban centers or point sources. And this was a particularly interesting effort in that we had to use satellite-derived measurements together with the limited surface measurements we had, because this project was really conceptualized as far back as 2015 and or even earlier. And it was a time when we didn't have extensive surface PM 2.5 measurements. So this work here discusses the methodology itself. These are the stations that are set up at 11 locations, north, south, east, west, transect, some sites in central India as well. And we've made every other day 24-hour measurements in 19 and 20. So a massive effort, and it's a pilot in some senses to really allow us to augment, national aspirations of surface measurements across the entire country to, 800 odd stations or so, perhaps even 1,500. And this uses a speciated sampling system. And these are, of course, time integrated measurements, but multiple chemical entities from various channels, about 50 or so chemical species that will allow for a meaningful source apportionment effort. I just want to show you a small snapshot. All of these locations, I said, were explicitly chosen to be regionally representative. Mohali and Rohtak, of course, will be regionally representative of the region in northern India that's quite heavily polluted. But other than that, these are all reasonably unpolluted regional background sites. And you can look at the concentrations at each of these locations. This is the 2019 average and the percentage exceedance, of about even twice the max, except these two sites, Mysuru in southern India and Mahabaleshwar, which is a high altitude site in Maharashtra. There is substantial violation of the max, which is to really say that the background concentrations of PM are quite high. Peter made the point about different sectoral shares, seasonality in these shares. We used a combination of in situ PM mass measurements, the emissions inventory and trajectory ensemble analyses to get sort of a first cut approximate of the primary anthropogenic source emissions shares at these various locations. And you can see these sectoral differences going from northern India to southern India. The message here is northern and eastern India, open burning, agricultural residue burning is a fairly important component, whereas in southern India, industrial coal emissions seem to dominate on an annual average basis. And residential biomass, which is indicated in this grayish sort of blue, is prevalent across the country. There are, of course, differences in the sectoral shares as a function of this season. The message here is if we are really thinking about source control strategies, we would have to go after, open biomass burning, residential biomass, and of course, much more organized government policy decisions to take a look at coal combustion from electricity generation. I don't want to go into the specifics of these setups, but I'm just pulling this up to give you an indication of where do the more involved measurements of speciation, size distribution go into supporting, understanding source-specific climate radiative effects, where you can really couple the standard receptor modeling implementations which guide air quality management decisions in terms of source control and go after even mixing states by certain hybrid approaches. So there are great opportunities to leverage existing measurements, supplement them with more time resolved and speciated measurements, size distribution information, etc., to really help achieve these optimization frameworks of enhancing air quality, climate health co-benefits. Other things that we can do is really ensemble averaging, bottom-up and top-down approaches, the CTM and receptor model outputs, look at how they all perform against one another, how the ensemble performs, and then really use these as more robust indicators to both constrain uncertainties and also to go after, the really most relevant sources, things that you might get more bang for your buck, if you will. Finally, I just want to talk about the importance of leveraging satellite measurements together with in situ measurements in various approaches, including statistical approaches. This is just an example. There are lots of studies out there that really show us how to leverage satellite measurements. You see, satellite measurements come with their limitations and uncertainties, but they also have a spatiotemporal coverage that cannot be achieved just by in situ measurements. So hybridizing the two to inform various things, including, obtaining exposure assessment at, these kinds of spatiotemporal scales, driven by country-specific in situ information, might actually be useful even in enhancing things like the GBD estimates for PM-induced adverse health effects. So I'm going to put down a few points and then, of course, request my co-chair also to comment on them in terms of the priorities for air quality management in India. We'd, of course, need to establish long-term trends network, not only for enhanced measurements, but also to meaningfully assess what the benefits of policy interventions and mitigation actions that we put in place are. Are we really obtaining the benefits that we expect to obtain from certain policy decisions and control strategies that we implement? The NACS review, especially for eco-sensitive zones, I've already spoken about it. I think all of the evidence need to be assembled to understand whether or not there's a case to have more stringent PM standards. There is a policy document for this National Clean Air Program that really talks a lot about and details very specific actions to keep, to sort of bring non-attainment zones into attainment. But there's really very little detail or even discussions on how to keep attainment zones in attainment. And I'm really talking about, non-urban regions. And we know that in India, air quality problems are not just an urban center problem. Rural regions also experience very, very poor air quality. And there's a recent publication in PNAS that quite nicely outlines the problems of PM-induced air quality deterioration in rural areas as well. And if we go to a new NACS, which will probably be more stringent than the existing NACS, then we really need good strategies to really keep compliance zones in compliance as well. I've spoken about some of the weight of evidence ensemble approaches to develop these plans and strategies. And another opportunity is really creating a central repository that integrates not only air quality data, but also leverages things that are filed for environmental clearance in, large national projects and the air quality parameters that are reported in those EIAs, and also integrating it with, information like hospital admissions, mortality, morbidity data to really do effective exposure assessments. Other opportunities are, and we spoke about low-cost sensors. They're a great tool for secondary data. They're probably not yet sufficiently advanced to be used as a regulatory monitoring instrument, but this is a great tool for enhancing, encouraging, cultivating citizen science and building a secondary data repository. And this is an item that I saw in the panel discussions in the chat box. At least in the context of clean air, there are very many socio-cultural barriers to actually achieving, whatever the mitigation actions and source control actions that are set out either by individuals, groups, or policymakers. And this will require trans-interdisciplinary teams if any of these actions are actually to be successful. I can give you some instances of, gender divide, cooking in rural households, and some, outreach experiences where we did some spirometry experiments and showed them theoretical and actual lung ages. It didn't bother the population so much that their women were suffering, but it seemed like a really big problem that their kids and especially grandsons were bearing the brunt of exposure to poor air quality. We can either be enraged about it or really look at these socio-cultural constructs as opportunities to enhance public awareness and really bring about the air quality changes that we desire. So I'm going to stop with this and request my co-chair to sort of take over, chime in, and we'll sort of have some concluding remarks in the session.
Ramya, thank you so much for your overview of the situation on the ground. I really appreciate you sharing your experience and thoughts. At this point, we're going to just continue the discussion, and we're open to answering any questions from other panelists or the people viewing. I can start off with a question for you. You mentioned just now the role of low-cost sensors. I mean, this is a really emerging technology that many people are adapting. And earlier in your talk, you mentioned the need for about 4,000 to 5,000 measurement sites. And so the question is there a role for low-cost sensors if the technology can be proven or improved as a robust monitoring in a regulatory context? Is there a role for low-cost sensors to fill some of that gap between the less than 1,000 to the 4,000 to 5,000 that are required?
That's right. I mean, there are already pollution control boards that have really embraced low-cost networks to sort of complement some of their efforts. I think this is really a tightrope walk at this point. Low-cost sensors are attractive for a variety of reasons, not just the cost itself, but simply the ease of operation and the voluminous data that it will spit out, right? I think so far as there are adequate caveats to understand what these measurements should be used for or not, they're a great tool to give you a ballpark estimate of what we have. But I don't think the science is sufficiently mature, and it has not been adequately tested in a variety of airsheds in India to really be embraced as a regulatory tool just as yet. So there's been extensive testing, calibration in urban hotspots, and they seem to be doing reasonably well. But that's also because of the kind of pollution mixes that you have and the fact that they far, far exceed, the detection limits and the threshold concentrations of what some of these, tools might be able to do. So I think, yes, there's a role, but I think it should not be very aggressively pushed, because I actually fear that the pollution control boards are more open to adopting this, perhaps even at the expense of more rigorous regulatory tools that we'll really need to make careful decisions.
That's a fair point. No, I want to build from something you just mentioned. I think the calibration aspect and what we talked about and what the previous panel actually talked about is these low-cost sensors are measuring particles optically, and as we know, that's a function of composition. It's a function of relative humidity, how much black carbon is absorbing versus scattering components. And so it adds a huge complexity. If you don't have a kind of uniform mix, or if there are changes seasonally, it will skew the data in one way or another. And so, yeah, I think they're a very useful tool also for education and bringing awareness to people. If they have a sensor that's near their home, they're more likely to see what the levels look like. Even if it's not accurate, it builds a community of people who are interested in the problem. And that makes large inroads in trying to solve the problem. And so I think that's another important role for those low-cost sensors. But I 100% agree with you that they're not quite ready for regulatory prime time. I can't hear.
Sorry. I mean, I think we should really start putting together a database of these low-cost sensor measurements. We will get smarter, and we may even be able to do post-facto corrections and things like that. So it's useful to collect, consolidate, and archive that data. It's just not ready for, a regulatory use just as yet.
Yeah. We don't have a lot of time left, but I have another important question for you. And I know that we probably have biased answers given what we do and our focus on measurements. But one of your slides in the Coalesce project, it's bringing a lot of pieces together: emission inventories, measurements, modeling, and assessment. In a limited funding situation, and you only had to target one or two of those, given that they're all important, what would you think is a major gap right now that we need to fill in order to move everything forward?
So, like you pointed out, I am tending to a natural bias. So I think that once we stabilize sort of the emissions inventory building effort and the EFs, and that's a pressing need right now because there's a lot of even retrospective measurements that are available, which are not properly exploited because we don't really have country-specific feel for some of these underrepresented sectors. There's a lot of plug-and-chug speciate profiles going on, which is probably resulting in findings that are not only particularly relevant, but in some instances also misleading, okay? The other thing is the modeling effort is absolutely important. And I think fixing these inventories is going to cater to both of these things. What we're really starting to find specifically with validation of these modeling implementations is we simply do not have compositional information at all to understand what is right, what is going wrong, and how we might, better parameterize these things, even for the climate models and, the physical-chemical mechanisms that are lumped together, ill understood, etc. We're not going to achieve that without a critical mass, if you will, of time and composition speciated measurements. So if you really have to put your money somewhere, I would say let's increase the emissions factor measurements effort, and let's also augment well-speciated quality control measurements to really allow for validation of the other things that we are doing.
I agree. No, I think that was well put. It looks like we have a question with a little bit of time to answer. Is there a comparison between the impact of methane emissions from landfill sites, dump sites, which can also cause particulate matter pollution due to fires and landfills, with other impacts, solid waste, garbage mismanagement, like particulate matter from localized burning? That's a question I don't know if that methane emission would get lumped into, it would kind of be separate question, I think, with a climate relevant thing. I don't know that the methane is what's actually starting landfill fires. I think some of those are intentional, some of those happen unintentionally, but that's also typically treated and kept separate. So I don't know of any studies that kind of link the two. Ramya, do you have any thoughts on that?
I'm not really familiar with the literature that sort of links these two. I suppose the question alludes to spontaneous combustions and maybe PM generated from such combustions or the secondary particle loading as a consequence. I don't immediately have a feel for specific measurements that have been made, but there are lots of landfill burning and emission studies, which also quantify the co-pollutant gases. So that might be a point to really look at connections and perhaps estimate what that combined load might be or a comparative load might be.
Agreed. Great. Well, I think we have hit time, so we should leave the panel open now for the next group to come in. So thank you again for your presentation.
Thanks, everyone. Thank you.